Hi guys, today we're going to talk about covalent bonds. Let's take a look. So reminder, covalent bonds are between nonmetals. If we see a metal, that means that we have an ionic bond or a metallic bond. So here we're only going to see those elements that are nonmetals. These electrons are going to be shared, not a transfer of electrons, shared. So no ions here. We'll talk about polarity in just a little bit, but no ions. So this means that these guys are going to be mostly insoluble or semi-insoluble. Equal sharing is going to cause non-polar bonding. An example here would be like hydrogen sharing with each other, as you see in the picture. And unequal sharing is going to be a polar bond, as we see here between hydrogen and fluorine. The reason that happens is because electronegativity. Two hydrogens together have the same electronegativity, so the difference in electronegativity is 0. However, between hydrogen and fluorine, we know fluorine has the most electronegativity on the periodic table, and hydrogen has very little, so the difference between the two is a lot. So fluorine is going to overly take that electron more than hydrogen's going to have it. They're still sharing, just fluorine's getting more than their share. So remember I talked about it would be like if friends combine their money equally to buy a bubble tea or a coffee or Ben & Jerry's or something like that. But one friend drinks more than their half of that beverage or ice cream. So polarity forms when electrons are pulled closer to one atom more than another atom, and the electrons are going to be pulled closer to atoms that have higher electronegativity. So if the electronegativity is the same, then they're going to share it equally. If it's unequal electronegativity, then they're going to share it unequally. So really ionic bonding is just the electronegativity is so strong in one atom that it pulls the electron over all the time. And so instead of sharing, it's a transfer. You can think of it as not even extreme sharing, beyond extreme sharing, right? All right, so polar molecules are going to have a positive and a negative end. We've been talking about this, like those batteries. And when we have something that's polar covalent, we know that they don't go into being ions where one is just totally positive and one's totally negative. Instead, we have these partially positive, partially negative ends, and you've seen me make this little symbol that you see here on this water molecule, the Greek symbol there. And we call this a dipole moment. And that's where a molecule is going to have that partially positive, partially negative charge there. And water is a great example. Definitely covalent. Oxygen and hydrogen are both nonmetals. But because oxygen is more electronegative, it's going to pull those electrons over to its side a little more often than hydrogen is. So here's a reminder of where our electronegative elements are. Remember, we're not memorizing these numbers, even though the numbers are there to give us some context. We're really looking at those trends and understanding why they're electronegative, because they have fewer energy layers there with the electrons, so they're smaller. There's less shielding of electrons between other atoms' electrons and that nucleus, and the strength of the nucleus. So as we go across the periodic table there, across the period, the row, we see that that electronegativity gets stronger because we're adding more protons there without adding more shielding or layers of electrons. All right, covalent bonds are a little extra fun because we can have multiple bonds. We can have a single, right there, single bond, double bond, or a triple bond. Single bonds are the weakest and longest bonds. Double bond is medium strength and medium length. And then a triple bond is going to be the shortest bond, so the shortest distance between those two atoms, and it's going to be the strongest. And this just makes sense if you're holding one hand with a friend. That would be like a single bond. And if you started spinning around in a circle, it would be easy for you guys to break that bond and spin off there. But if you're holding two hands, double bond, spinning around, it's going to be harder to let go and spin off. So just an example there. All right. Naming covalent bonds is so much easier than those ionic bonds. Basically, we just take the number of atoms that are present and we add a prefix. So here are our prefixes, and a lot of these are prefixes that you already know. Like, you know, tri means 3 from triangle and tricycle. Tetra means 4, like Tetris, that game, 4 blocks, tetra. Penta, like the pentagon, means 5. Octa, octagon or octopus, means 8. Nona, 9. I think it sounds like 9. And deca, decade, means 10. So a lot of these we already know, but those are the prefixes that we're going to use there. And our formula writing is that we just write how many we have there. They're still going to bond to get octet rule, except for hydrogen and helium, you know, and those noble gases aren't going to bond with anybody. So if we look at this example here, we can see how easy it is. If we have diphosphorus pentasulfide, we're going to write the formula P2S5. So the prefix tells us the number of atoms for the name that's on there. And pentasulfide, here we have 5 sulfides, so sulfur with a 5. Now here we see carbon, even though there's only 1, we don't write mono. We only use mono for the second word. So I think our next slide says that. No, it doesn't. So anyway, so naming, same as ionic compounds, where but we're adding prefixes and we add "ide" to the end of the second one. So here we go. Here's the slide I was looking for with that mono thing. So mono, we have carbon monoxide. So we don't say monocarbon dioxide. We just say carbon dioxide. We don't put that mono on the first one. But here, if we're looking at carbon monoxide, we do put that mono on the second one. That's the only little caveat rule that we have in covalent bonding. And then covalent bonds, we do have some common names there, like water. We don't walk around saying dihydrogen monoxide. We just call it water. And ammonia, we don't call nitrogen trihydride. We just call it ammonia. And then here we have some examples. So what do you think that first one's called? All right, we have, let's see if I can move in here. We have sulfur dioxide. How about the next one? N2O4. Dinitrogen tetraoxide. And our last one, oops, it's fighting me. There it is. Nope. Well, anyway, it's boron. It doesn't want to move. Boron trifluoride. And if you go into our slide deck and you click here, there's a little additional cute YouTube thing you can check out. All right, guys. See you next time.